This animation will illustrate the application of Gauss's law to the case of a uniform long straight line of electric charge. Recall that Gauss's law relates the total flux through a closed surface and the amount of electric charge enclosed within that surface. A line of charge is characterized by a linear charge density, that is, a charge per unit length. It also has cylindrical symmetry. The electric field will share the symmetry, and so the electric field due to a positive long straight line of charge will be directed radially outward from the line of charge. In addition, this symmetry means that the electric field strength at a given point can only depend upon that point's distance from the line of charge. Consider now a cylindrical Gaussian surface centered on the line of charge. The surface has a given radius and length. To evaluate the flux integral for Gauss's law, we will consider separately the contributions for the flat end caps of the cylinder and for the curved cylinder portions of the surface, or the can. First, consider a patch on one of the caps. Since the electric field is perpendicular to the surface normal vector, the result for E dot dA is 0. As a result, the flux contribution for any patch on the caps is 0. Because every such patch has 0 flux, the net result of integrating the contributions of the flux from the caps will also be 0. Now consider a patch in the can. The electric field is parallel to the surface normal, so that the contribution to the flux is fairly simple. Furthermore, since every portion of the can is the same distance from the line of charge, the radial component of the electric field is fixed. Integrating the flux over the can becomes simpler because the electric field component can be factored out of the integral. The resulting integral is just the area of the can portion of the cylinder. We can now combine the results for the caps and the can to obtain the total flux. The total charge inside the Gaussian cylinder is easily determined from the charge per length. Now we use the flux and charge results in the two sides of the Gauss's law equation. The result relates the radial electric field to the linear charge density of the line of charge. Since this result doesn't really depend upon the details of the Gaussian cylinder, some simple rearrangement provides the electric field as a function of distance.